शुरू करिए.
Good morning, all. So today I'll be discussing about the symmetry and the topology in the quantum material, and this is probably the field in the of the condensed matter physics, the topology and symmetry in the quantum material, which is one of the hottest topic around, and enormous amount of work is going on around the globe, and probably it got the attention with a paper from Maryland, the topological insulator in the 3 dimension by Mealy and Jean, which actually an extension of the idea of the integer quantum Hall effect discovered by the Van Paging in 1985. And today, what I would like to tell, what sort of work has already been done in a brief overview, so to say, because it's not possible to summarize the work, 15 years of work within one presentation. And in addition to that, I'll just like to shed some light on what sort of direction this field is actually moving towards in future, and what sort of promising prospect a young researcher could possibly have along this field. So by definition, symmetry, these are two, symmetry and topology are a very important concept as far as the physics is concerned. It actually helps us to understand the more complicated problem in much easier way. So by definition, what symmetry says, it is sort of operation that leave the system invariant, like a translation, rotation, and all that. However, topology is another branch of mathematics and very less familiar as compared to symmetry. So, at least in the elementary level, topology is a branch of mathematics that deals with the property of the space that remain unchanged under continuous deformation, like stretching or bending of a rubber set. And it has a one-to-one correspondence with the condensed matter physics, and that is what makes this field of research so much exciting and challenging also. So the first condensed matter counterpart, what people have often encountered along the line of the integer quantum Hall effect, is the topological insulator. It is not of an insulator, of course, along with some very well-known insulator. The first one was, let's suppose, band insulator. Example is a diamond. Another one is a Mott insulator. The insulating property here possessed by the material due to the strong electron-electron correlation, so to say, repulsion. Likewise, Anderson insulator, the hindrance of the flow of the electron due to the presence of impurity. Kondo insulator, it is the presence of the scattering of the electron due to the magnetic impurity. So these are sort of different types of insulator one material scientist would encounter, or physicist often encounter in the condensed matter domain. However, this topological insulator is totally different. So it is sort of an insulating in the bulk, but it conducts electricity on the surface. This is sort of weird property, and people believed and probably have explained it theoretically and verified it experimentally, that this is this has to deal with the topology of the electronic wave function associated with the materials. And this is one thing. Next is the topological phase, like what we have often encountered in our usual phase transition domain, like solid to liquid or ferromagnetic to paramagnetic. This is another sort of phase transition. Usual phase transition involves change of order parameter or a divergence of order parameter across the phase at the phase transition point, and restating it in the language of the symmetry, symmetry changes across the interface of the phase transition across the border. Let's suppose from ice to water, you often change the symmetry. In one case, you have rotational symmetry, translational symmetry. But in another case, you do not have rotational symmetry. In magnetization case, the rotational symmetry or the spin rotational symmetry usually breaks in the spin momentum space, or from paramagnetic to the paramagnetic phase transition. But this is the topological phase transition, is a unique phase transition where you do not often encounter such scenario. Instead, this is something has to deal with the energy gap. And this phase is also otherwise known as symmetry protected topological phase. This topological phase has a unique property. They actually very much robust against external impurities, uh, and they don't often change their physical property and responses. And this unique property is just the output of symmetry preserved by the material electronic wave function in their momentum space or in real space. So that is why this is otherwise known as symmetry protected topological phases. So these are very, I mean, one can explain it hour and hour, because enormous amount of study have been undertaken on each of these topics. These are very vast topics, but I just want to give you a brief overview, and my main focus would be where do we stand in terms of research of quantum material in terms of topology and symmetry. Now, so these are the symmetry as I said, and oh, I'm sorry. So here we'll see how I can change this. Okay. Yeah. So symmetry breaking. In previous slide we have discussed how come different phase of the material can emerge due to the different symmetry and topology possessed by its electronic wave function, and have been explained by the band theory. And now we will encounter and we will discuss something related to symmetry breaking. It is a very much fundamental concept, and we know most of the exciting and diverse phenomena happens in the universe, starting all the way from high energy to low energy physics, is nothing but the breaking of the symmetry in one way or another. So first one is the spontaneous symmetry breaking, which is very often encountered by the physics people, and probably the idea have been borrowed from the high energy physics. People have used it in ferromagnetism in order to explain the ferromagnetism in condensed matter setting, and in a high energy physics, you know, the very famous Higgs mechanism. But what sort of other aspect one can expect from the symmetry breaking is a quasi-particle. Any types of a quasi-particle, let's say phonon, photon, plasmon, magnons, all those are sort of a quasi-particle, and they are the consequence of the symmetry breaking. Likewise, order phase. If you go from the digital to order phase, that also is the reflection that symmetry breaking is taking place. Likewise, phase transition, it is also another consequence of symmetry breaking. And the very famous Higgs mechanism, the mechanism which is responsible for the acquire of mass of almost all the elementary particles. And then topological phases of the matter. Here, as compared to all the previous 5 different cases what we have discussed, there it is very normal sort of thing. But in topological phases of matter, one might immediately ask what sort of symmetry breaking associated with this. It is very familiar time reversal symmetry. But other things you may encounter different crystalline symmetry, other such as gauge symmetry, many different sort of symmetry. Now concentrating on the topological aspect of the matter. This is something what we have discussed it many times, but just to revisit it, we know it. If I start from the figure A says, it's a topological band inversion. If you look at the figure A, now imagine a diamond, and this is how they have been represented in terms of the band diagram. or you can call it dispersion relation. So it's the energy in relation to the momentum. If the atomic limit, that means those band, conduction band and the valency band are at infinite apart from one another, then there is absolutely no chance to dislodge an electron from valency band to conduction band to make it conducting. That is our usual case of diamond, let's suppose, because diamond you need something around 6 electron volt. But putting it schematically, this is how it might look like. But if you want to idealize the situation, then go back to the Dirac vacuum, where all the valence state has been filled with the hole and the conduction band is empty. And you minimum need 2m0 c square amount of energy to actually create an antiparticle, so to say, in the context of experimental physics, or the finding of the positron. But coming back to the condensed matter physics, let's see, this is your diamond, normal band gap, 6 electron volt. Here, two atomic energy level, you try to bring them close together by tuning the momentum value. This is the momentum axis, and then you are trying to bring them close together. And this parabolic axis, why are they getting it from? And then after tuning this crystal momentum, or otherwise by tuning this lattice parameter, you can actually reach a position where these two bands touch on one another, and subsequently it may actually reverse, or we call it band dispersion. And this might happen in the condensed matter material like solid state physics by two factors. One is spin orbit coupling, another one is crystal field symmetry. So mostly these two things are intertwined in the material, and these are the two very important factors in order to achieve this band inversion. And band inversion is one of the necessary conditions in order to realize the topological phases of the matter, but it is not the sufficient one. And the question one might ask, is it the only situation where one can expect topology? No, there is some special cases where you may not need band inversion to happen. So figure B represents the bismuth telluride, the first three-dimensional topological insulator of bismuth selenide family, bismuth telluride. And then here you can see if you actually incorporate or include spin orbit interaction, you can see the band inversion. But without incorporation of spin orbit coupling, you have usual parabolic band, and there is an insulating band gap and nothing else. And it's sort of very narrow band gap of semiconductor. Narrow band gap means it is something that you can provide that much amount of energy to make it conducting, like some milli-electron volt sort of energy. But once you introduce spin orbit coupling, you can actually see the band inversion. This is the first principle calculation, theoretical calculus. Now coming to the figure C. Figure C is a textbook perfect Dirac one. And you see here, it actually follows two theorems. One is a concept called energy momentum locking. If in a normal material, energy and momentum, okay, let me put it this way. If you consider a copper wire as a conductor on the surface, in a topological insulator, the surface is also conducting. So then what is the difference? The difference is the electron that is flowing in the copper surface or in copper wire doesn't need to have a very specific spin reorientation. I mean, they do not have to have a specific reorientation with regard to their energy or flow. What we called as, what we often called in the domain of high energy physics as helicity or chirality. Okay, it is the projection of the linear momentum on the angular momentum on the linear momentum, so to say. And if the particle is massive, it is known as helicity, and if particle is massless, it is known as chirality. So that is why if this is my Fermi energy, and this is where my band gap lies, above the Fermi energy, you have this clockwise helicity, and this is counterclockwise helicity. This is what the textbook perfect Dirac one, and has been verified experimentally by an experimental technique known as angle result photoemission spectroscopy. This is nothing but the implementation of the photoelectric effect in order to mapping the energy of the surface electron in the three-dimensional range. That's what it is. So, but if you look at this, only you concentrate on the surface state. So this is how it will look like if you look at from upside. And now if you, with regard to this, in figure D, second figure, if you look at this trivial metal, actually, you know, in copper, where as I have mentioned, the number of, the probability of getting the number of electron having up spin is very much equal to probability of getting number of electron having the down spin. And that's what it is. So that is why in the copper wire, the electron which are actually traveling in the copper wire do not have a specific helicity. They're random. However, that is not the case with the topological insulator. That makes them totally different. One is very much prone to the back scattering and one is not. And putting it in a much more technical language, one possesses the pi Berry phase and one doesn't possess pi Berry phase. Okay. Now coming back to the figure E, I was telling you in the symmetry breaking slides that in topological insulator, what is pressure? In topological insulator, you can have the time reversal symmetry. Okay, because both time reversal symmetry and the surface time reversal symmetry may preserve and can be broken. So in topological insulator, this symmetry has to be preserved. In addition to that, there are many materials can be and probably have been also have been identified till date that they possess different sort of symmetry, mirror symmetry, crystalline symmetry. They are known as a topological crystalline insulator. And here you look at these 2 points, K point and M point, they are known as a sort of high symmetry point in the Brillouin zone. And you can call it, these are time reversal invariant momentum point. This is the point at which the time reversal invariant, the momentum is time reversal invariant. And if you know further, then you are very much familiar with the Kramer's degeneracy theorem. And the ground state is at least two-fold degenerate provided the system possesses the time reversal symmetry. And these are these 2 points, high symmetry point in the Brillouin zone. Okay. Likewise, if you extend this concept provided the system exhibit mirror symmetry, one is the mirror reflection of another, and this one is the mirror reflection of another. That is why you can call the higher order topological insulator. And what is higher in this case of because here in this material you see the number of Dirac cones are sort of a multiple of this single one. It is 4 times. It is even 4 times. But this either it can exhibit mirror symmetry. It is another crystalline symmetry. And this is rotational symmetry. So in either case, you can have a higher order topological insulator. Then you can ask me as an experimentalist, what is the use of this higher order topological insulator? If you do have a higher order topological insulator, then your conducting channel will be multiple of that. So now suppose imagine I have a single Dirac cone. That means I have a single edge state or single surface state. But if I have higher order topological insulator, like as I have, you can see in the figure G, you can have 4 times more conducting channel. So your conductivity will be more pronounced. Okay, that is what people have been striving to.
Yanti,
yes.
Will the number of conducting channels in the case of mirror symmetry and C4 rotational symmetry be same, or will they be different?
Not always. C4 symmetry, we have considered here the symmetry theta is 90 degree. C4. Okay. But mirror symmetry also possesses this. But if the molecule or the system possesses some diagonal symmetry, here also another cone you may get. It will become 6. But this will not be like that. It will remain 4. So sometimes it may actually match one another. Sometimes it may differ. It depends upon the material, the symmetry possessed by the material.
Okay, so can I say that, so let's say you have some underlying symmetry group. So the more
Yes.
number of elements imply the more number of conducting channels. Is this true or not
Yes, yes.
necessarily?
You are correct. You are correct. But being an experimentalist, you have to take this in a very serious way. That this Dirac cone here you can see these are smaller figure, just to make you feel this has to be as close as to the Fermi level. Then only its topological feature can be very pronouncedly be realized in the application point of view. You can have multitude of Dirac cone. You can have multitude of while cone or while particle, quasi particle or Dirac quasi particle. If they are far away from the Fermi energy, then their contribution or their effect as a topologically non-trivial uh, material will be very less pronounced. It will be buried in the background of a ball of effect. That's one thing you have to take care. Otherwise, whatever you are saying, that is correct. And moreover, another difficulty material scientists now facing is if you have a multitude of more number of these, it is extremely difficult to manipulate them as per your will. Therefore, the ideal condition is at least one, at best two, not more than that.
So can I ask one very naive question? So what decides the number of such cones in a material?
That's a very good question, and this will be essentially decided by the symmetry.
You mean the crystalline symmetry?
Yes,
what sort of
very
crystal
much.
is made inside the material?
Yes, you are right.
Achha.
You are right. Because here you see, suppose these 2 points are actually minor band gap. I am telling you it is a narrow band gap semiconductor. Okay. So let's suppose to have a field. Silicon is 1 electron volt band gap. This will be half of this. This will be half of that. Okay. So here, if I can actually add one magnetic element, then you can actually introduce a more band gap in this system. If you look at here, or
Yes, I am. So somehow I was not able to hear your sound on my system. So could you please repeat that again? Okay, yeah.
okay. So anything else, Ralbhai?
No.
Okay.
Yeah. So far this much only.
Okay. So now this is already I have explained. We need to go for it. Now, I was explaining in the previous slide that band inversion is a necessary condition in order to realize the topological feature in a condensed matter system. However, it is not the sufficient one. The sufficient one is, in addition to the necessary condition, you have to have a topological invariant, like J2 topological invariant, because the parity of the wave function in the momentum space also possesses either +1 or -1. That is why J2 equal to 0 or 1. For conventional insulator, J2 is always 0. But for topological insulator, a strong topological insulator, so to say, it is 1. So now you see, this is my energy momentum dispersion relation. This is where the band touches, even in fact crosses each other. And these are 2 points. You see, these are 2 points. And these 2 points, actually these 2 points. Can you see here the cursor? Dirac Semimetal or Weil Semimetal. These are two point here. But this is another thing. This is called chiral crystal, or it has another name called Kramers-Weil fermion. This Kramers-Weil fermion doesn't need band inversion to happen. So it possesses something called chirality, and this special characteristic, and it is tuned by spin orbital coupling available in the system due to large atomic number element present in it. And that is why the very important question people often encounter and asked, is band inversion is a necessary and sufficient condition for a topological feature to realize? The answer is no. There are some systems which you may not need to have your band inversion. And coming back to the Dirac semi-metal, this is fourfold degenerate bands, and these are 2 points. And from the very conventional definition of a band theory, the point at which band touches each other is known as semi-metals. And since this material possesses the linear dispersion relation E equal to Vp of some sort, so that is why it is known as, and this low energy quasi-particle follows this Dirac equation. It is known as Dirac quasi-particle, and material possessing this quasi-particle is known as the Dirac material. Since band touching one another, it is known as semi-metal. Hence, the name is Dirac semi-metal. What sort of symmetry it possesses? It possesses inversion symmetry, time reversal symmetry, in addition to the crystalline symmetry. What sort of crystalline symmetry? Sort of rotational symmetry it possesses. Now, if you actually want to tune this.
Can I ask one more question?
Yes.
So here in the context, here in this case, you said that band inversion is not a necessary and sufficient condition for topological behavior to exhibit.
Yes.
So are we aware of such necessary and sufficient conditions that if they are there, then it will exhibit topological behavior, and if topological behavior is exhibited, then that condition must be there. Are we aware of such conditions?
No, we are not. We are not. Whatever in laboratory we have experimentally verified, people have experimentally verified and theoretically proposed. They are telling the elemental definition says, first, it has to have a band inversion. Second, it has to have a non-trivial topological invariant. Like as I said, theta equal to 0 or pi. Pi is the very phase associated with the electronic wave function. But apart from that, then people subsequently realize that there are some material where you may not need this band inversion, and that goes under the name of a Kramers-Weil-Fermian system. Okay. Where the chirality of the system or the molecular structure will play that role, and it can be tuned by the spin orbit coupling, the way it can be done in the this topological insulator by band inversion also. But you are asking, do we have such condition or criteria where system doesn't possess any of this but still exhibit topological feature, right?
No, my question is, so for example, so in this case, band inversion is ruled out. So band inversion turns out to be not a sufficient and necessary condition. So my question is, so are we aware of any such property? So for example, let that property be P. So if P is there, then the material will exhibit topological behavior. And if topological behavior is exhibited, then that property must be there in the material.
No, that property has not been verified. They're telling necessary and sufficient condition. But you are asking for something very, very mandatory condition, and which is very much available in almost every topologically non-trivial material.
Yeah, this is what we mean by necessary and sufficient condition. This is the meaning of necessary and sufficient condition.
There is not unique condition. There are two conditions here. Necessary is band inversion, sufficient is non-trivial topological invariant. That is first category. But people subsequently realize there are some material where band inversion is not taking place, but still they exhibit topological property. Okay. Then it actually proved them wrong, that probably band inversion may not be the urgent requirement of the topological feature.
It's not sufficient. It's not sufficient.
It is certainly not sufficient. So then they have put it in terms of chirality. Probably this is coming from the chiral feature of the structure associated with the material. So these are two features. In one case, band inversion is available. In another case, band inversion is not available. Yes. In the second category, you need chirality and spin orbit coupling. In first case, you need topological band inversion and topologically non-trivial invariant, topological non-trivial invariant.
Okay.
Yes, yes.
Okay,
So
thank
Dirac, yeah, Dirac semi-metal. Okay, if it is a four-file degenerate band touching at a single point in, as I am mentioning, time reversal invariant momentum point. If you break the inversion symmetry or time reversal symmetry, you will end up with while semi-metal where two while fermions and they do have a different chirality, and the positive and negative sign is just a schematic, is a schematic depiction of magnetic monopole in the momentum space, and their separation is actually give an indication that the semi-metal is stable, stable. And the only way you can bring them together is just tune the spin orbit coupling by tuning their lattice parameter and spin orbit coupling strength. And if you can bring them together, you will end up with a Dirac semi-metal. But if there are certain material which have the planar mirror symmetry or planar symmetry, then you can end up with a line. And they call it, I think, nodal fermion. Instead of a single point, you have a line. And here also you can see the very phase is still pi. That means these are also topological, non-trivial. This is another kind of fermion. It is higher order higher order fermion. This is Dirac fermion, this is Weil fermion, this is nodal fermion. Then double Weil fermion, threefold fermion, fourfold fermion. There are different level of fermion. What I was telling you previously, if you increase the number of Dirac pole, then you are actually increasing the number of conducting channel, because there is a theorem called bulk boundary correspondence. The number of edge state is very much equivalent to the number of times the actually electronic wave function wrap around the Brillouin zone. That is the analogy as far as the topology is concerned. So these are higher order fermion. People have really trying hard enough to come up with this kind of material where even conductivity of the system is much faster, where the mobility will be extremely high, and so that it could be useful in the upcoming Spintronics devices, they call it. So topology in Spintronics. And these are some basics, and probably the groundbreaking discovery happened in 2015. This is the tantalum arsenide, which is the band with the arrangement of tantalum arsenide. It happens to be the first experimentally verified condensed matter system to have exhibit the Weil semi-metal or Weil fermion. And these are their corresponding. And you can see the 12 group, 12 Weil fermion group point, 12 Weil, like this, there are 12. So it is very difficult to tune them. But the fortunate part is, since they're really close to the Fermi energy, it could be mapped actually by using angular photo emission spectroscopy. Had it been not the case, if they would be actually far away from the Fermi energy, then you may not able to see them by using RPS. So that is the difficulty always associated with the topological materials. So that's why here in this summary, in this slide, I just want to infer a conclusion saying that you see how brilliantly or cleverly the nature has taken care of the system by considering the symmetry into place. I mean, symmetry plays such a decisive role. In one case, you may it may give you a beautiful group of properties, but in another case, after breaking it, you may end up with another group of emerging and exciting properties. So that is why, in order to actually probe this very complicated domain of this topology and condensed matter setting, one really has to look into the system from the symmetry perspective. Okay, this is what I have already explained. So this is the main thing where we are heading into. I mean, okay, we have learned this much thus far. Then what is next? What is the upcoming research in the topology one can anticipate or expect at least? So now you can see the people have here. I just want to underline one statement. Whatever topological feature or material we have discussed so far, there goes under the name of a symmetry protected topological state. But there is another group of material called topological order. Topologically order material are much more robust, much more stable uh, as compared to symmetry protected topological states. Uh, Say for example, if you have a Dirac semimetal and you want to manipulate the Dirac quasi-particle as per your will, you have to take care of the three different symmetries. You have to maintain crystalline, I mean rotational symmetry. You have to maintain inversion symmetry. You have to maintain time reversal symmetry. And if you look at this thing, it restricts your application. You cannot introduce the magnetic element in it. You cannot actually introduce the achiral molecule or structure, because the moment you break the chirality, inversion symmetry is broken and it is no more Dirac semimetal. So the moment you are actually being restricted the number of symmetry, its application also being limited, also get limited. But in topological order, and another thing I want to say, in symmetry protected topological state, we have completely ruled out the possibility of the effect of the strong electron-electron correlation, which is inevitably there. Inevitably there. So, and the interaction between them cannot be neglected as far as the practical application is concerned. That is why the correlation between the topological state and strong electron-electron correlation will give rise these three different possibilities, at least as shown in the figure A. Topological magnet. You know why I am telling the strongly correlated electronic system? Because to have a magnetic system, there has to be a long-range magnetic order. That means spins are entangled. You can call it in a fancy way. And interaction among the electron is essential in order to establish the long-range magnetic order. In addition to that, if it has to possess the topological non-triviality, then one has to understand how the topology gets affected by the strong correlation, electron-electron correlation, or vice versa. Then this is CDW stands for charge density wave or spin density wave. This is another feature, which is the periodic modulation of the charge or spin inside the material due to the topology as well as correlated electron, strongly correlated electron. And then topological superconductor. Again, in superconductor, as far as vicious theory is concerned, unless there are two electrons forming a Cooper pair, there is no chance of realizing superconductivity. That means electron-electron correlation is must. In addition to that, you have to prevail the feature of the topology. That's why you always need to understand in the basic how does electron-electron correlation affect the topological feature, which is very, very new to us, and people have been trying to understand it. Then wave function and geometry. Wave function and geometry, I mean, it's a totally new page. Let me tell you, in conventional system, there are 4 degrees of freedom. In particularly condensed matter system, we often encounter charge, spin, lattice, and orbital. These are 4 degrees of freedom. And combination of these 4, I mean permutation and combination of these 4, gave rise enormous amount of strange and unique physical properties which have been exploited by the material scientists over the years. And we have absolutely no clue what happened to those 4 degrees of freedom and how do they affect the topological feature. This is very much an unknown territory people have been trying to understand. Next, symmetry and dispersion. In previously symmetry protected topological state, if you just to have a feel, let me see. Here, these are Lorentz invariant sort of. They follow the Lorentz invariant equation. I mean relations. But if you come here, they are not of this type. Here, the Lorentz invariant thing doesn't follow by this material. So they are actually categorize it as a type 2. Dirac semimetal is there, while semimetal is there, and they call it saddle bond. That means the crossing of the band never happened in a straight way. The way, yes.
Could you please say a few more words about it? What was Lorentz invariant?
Lorentz invariant means they are telling let's suppose in dispersion relation.
Mhm.
Okay. So assumption is that in while equation quasi-particle has to be massless.
Okay.
Quasi-particle has to be massless. That is the I mean to say theoretical prediction.
Mm-hmm.
But you never see that as far as the condensed matter setting is concerned. Because no matter how brilliant your material is, how ideal is your synthesis technique is, always you are associated with a finite mass. But here
Okay.
in this type 2 material, I'll come to that. You probably are asking where this mass is coming out of. Why are they
No,
getting
actually
improper?
not that, but in what sense something was Lorentz invariant in the previous case?
No,
And
yes. So you see, Lorentz invariance, I mean to say, it has to follow the transformation equation, which has to, that means that Lorentz invariant or Minkowski, they all are coming from that light cone.
okay.
Okay, so anything which is moving slower than this or speed of light, it has to be within the light cone. Nah?
Okay.
In that sense, they are calling it Lorentz invariant.
Mm, okay. So maybe if we consider electromagnetic field tensor,
Yes. Okay.
F mu nu is given by del mu a nu minus del nu a mu. Okay.
Okay.
And
Okay.
so then you can construct some some scalar out of it. So let's say F mu nu, F mu nu. I think it will be
Okay.
zero. No, it won't be zero. It won't be zero. Will it be zero? It won't be zero. Yeah, it won't be zero. So so this is a Lorentz invariant quantity, and if you construct scalars out of dot taking dot product between vectors p mu for example, because they're also Lorentz invariant. So
Okay.
when you say Lorentz invariance or Lorentz something is Lorentz invariant, you mean that so a vector transforms in a certain way under Lorentz transformations. But the
Yeah.
dot product of that vector with itself, or for that matter with any other vector, will be an invariant. So that will not depend upon the Lorentz transformations. So when you say something is, so I did not understand what was Lorentz invariant.
Okay. So let me tell you the way I have understand it.
Mm-hmm.
If you go to this one, this is
Okay.
the touching. This is the touching of the valency band with the conduction band.
Mm-hmm.
Okay.
Okay.
If this is happening, they call it Lorentz invariant. It look like a light cone, doesn't it?
Okay. It may be.
It
Okay.
is.
Fine.
It is.
Fine. I mean, there is something which maybe I need to know before I can understand this. That's also
Oh,
possible.
okay. 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 But
That's fine.
that's what I am telling. This is how I have understood it.
Okay.
So whatever the theoretical description you are asking, I might not be able to convincingly explain you, but this is what I understood it. So
Mm-hmm.
the linearity in the dispersion relation is coming the way conduction band and the valence band touches each other here.
Okay.
Okay. However, in this case, these are
Mm-hmm.
no more electron and these are no more valence band and the conduction band. These are the specific electron and the hole pocket, which are actually touching in an inclined way.
Mm-hmm.
That is why they are calling it type 2.
Okay.
This is the difference in the condensed matter perspective,
Okay.
nothing else.
Okay.
And whatever theoretical side you are asking, that I have to look into. In
Okay. Fine.
what sense? But one thing I know, it is associated with the effective mass of the quasi-particle.
Okay.
Because
Okay.
because how the relativistic particle moves essentially decided by its mass.
Mm-hmm.
Is
Okay.
it not? Whether it will be in the light cone or whether it will be outside the light cone will essentially be decided by its mass.
And if it's massless, it moves along the light. It moves along the boundary. If it is massive, it moves inside the light cone.
Yes, yes,
Okay.
yes. In that way.
Okay. Fine. Okay. Fine.
But of course, you can see, and if possible, next time I'll see what extra I can get. I would like to share.
Okay. Thank you.
So okay, this is the symmetry and dispersion, because dispersion is no more the way it has occurred in the previous group of material. Then next generation spintronics. This is silicon, another allotrope of the I mean silicon, where the spacer can be used, and the topological feature can be utilized here just to make an effective transportation of the data. They're calling it next generation spintronics by using the silicon. And
Uh,
then no,
Yanti, one more question.
yes,
So by the name, by the name, I get a feeling that silicene. So
it's a graphene sort of.
yeah. Exactly. Some one-dimensional sort of.
Exactly. Very right, very right.
So
It
how
is
do they make it? They make it the same way they make graphene?
exfoliation.
Exfoliation. Okay.
Yes,
Okay.
atomic layer exfoliation. So, but they are using your Scotch tape or not? I am not sure.
Okay.
And then FH, novel electric and magnetic field response. And you know that Carey effect, Faraday effect, the rotation of the angular momentum of the light in presence of the, or the change of angular momentum of light in presence of magnetic material. Okay, so one is through reflection and one is through refraction. So always the light angular momentum will change in terms of in the multiple of pi as far as the topology is concerned, because as I have explaining that topological quasi-particles are this non-trivial system exhibit pi Berry phase, and that pi Berry phase has to be reflected in the angular momentum of the light. And this feature will be very much useful so that we can use it in fiber optics and optical communication and data storage and all that. And the security purpose, whatever the people have been trying for the quantum computation. But quantum computation, cryptography and all that, they are using the superposition, coherence and entanglement concept. In addition to that, if topology can be added, it will be a great combination. Means as far as the security is concerned. And then yes, these are the diverse area, upcoming area as far as the topological quantum material is concerned. And in either of this field, whatever different sections we have discussed, the research is very minimal, and it is one can say at its infancy, and a very long way to go, and nobody knows how far this will keep on going. That is why it is an encouraging field and the time for young researchers to participate and contribute and enjoy. And the home tech message is this: the topological materials offer a unique chance to probe the fundamental science and a novel electromagnetic response like crystalline electronic state geometry. How does the electronic state is being affected by geometry? And the field's growth is anticipated to persist. Thank you.
Okay. Thank you, Gyanti. So let me give a clap.
Thank you.
So if you have questions, you may ask them now. If any of you, I've asked my
Sir,
questions.